Okay, so let's start. It will be in English because we have a lot of English speaker guests or even native English speakers. So welcome to the 2023 award presentation of the Dezső Dévényi Numerical Weather Prediction Award and the scientific presentation of the awardee of this year. I think we have around 15 participants online and around 12 or 13 here physically. So let's start. I am András Forányi and I will chair this meeting. I used to say that I had only one workplace, the Hungarian Meteorological Service, which is partly true, but in the last 12 years I worked at ECMWF, and so probably some of you know me, some of you don't know me. I had a quite close colleague with Dezső, so I had now the honor and the privilege to chair this session. And before we start, this is the plan for today. I will have 3 more slides about the award itself, and then my friend and colleague Gábor will speak about Dezső. So the idea was to give you a bit more information about Dezső, especially those who didn't know him. And Gábor prepared some slides for that. Then the highlight of today is the presentation of Máté, who is the awardee of this year. So I'll speak a bit more about him when we come to that point. So you are supposed to give a scientific presentation, and there will be a question and answer session afterwards. Then we will have the award presentation, because now we are physically here. The last few years it was partly when we were online actually. So we will present the award. I hope it's here, Gabi. Thank you. And then we try to close the meeting, and for those who are online, as we did in the previous years, there will be the opportunity to just informally chat to each other. I hope that's fine. But anyway, I start with a bit of history. As you know, that Dezső passed away in 2009. We organized some memorial meetings to commemorate his achievements in 2010. And also it was done by us, but also by the Met Society. I just put there the list of speakers, and the summaries of the talks of this 2010 event is one of these. It's here. Samples of the summary. Then we decided, together with the family, particularly Patricia, who is the daughter of Dezső, to have this kind of award. And we asked to prepare and design this award with this artist, Tamara. And this is the award on the photo. And maybe Máté will show us after his presentation how does it look like. We had so far 9 award winners until today. At the beginning, we gave the award every second year, and then we realized there was quite some interest, so we decided to give him the award on an annual basis. And before that, the award ceremony was part of the official celebration of the World Meteorological Day. It's an easy to remember day, 23rd of March. At the Hungarian Meteorological Service, or Hungaromed, as it will be called very soon. But then we decided that maybe that doesn't give enough spotlight to be together with this official celebration. So just the award was given, and that was kind of a small event. So we decided that on 2019 we have our separate meeting in the autumn, because Dezső died on Thanksgiving Day in November. And this also gives an opportunity that the winner can give a presentation and present us his or her work. And just I put there the members of the committee, Patricia on behalf of the family, Gyurka is on as close colleague of Dezső, and Gábor and myself, who were Dezső was our mentor and supervisor, and then Gabi joined us on behalf of the award winners, and Stan lately joined us, I think, last year, which is very good because there is a representative from the US where Dezső worked a lot. But more Gábor will speak more about Dezső himself and his stays in Hungary, but especially in the US. So originally we gave him Gábor 20 minutes, but Gábor worked hard to prepare a bit more, so I will be friendly with you and allow you a bit of more time, but not much more, please. Yeah? So I give the floor to Gábor, who will give you an account about Dezső, what person he was, and in terms of personal and scientific achievements. So, the floor is yours. Thank you, boss.
Okay, so I'm Gábor Radnóti, and I have the honor to give this introductory talk about Dezső. I have to apologize. Those who were here at the previous meeting, there is some overlaps. Each one showed a few pictures that are the same in my talk, but for the sake of the newcomers, I will still show them. So what I will speak about is who Dezső was, what he meant to us, and if I want to shortly summarize just with keywords, he was a teacher, supervisor, mentor, colleague, and last but not least, he was a good friend for many of us. As a cover photo, I chose this picture that was taken by István in November 2009, when by coincidence Dezső and István came to visit us to ECMWF at the same time. I think István came for a member state meeting, and Dezső came. He wanted to learn a few things, how they are done at ECMWF, and also we had some night together. So this picture could be easily in the library of ECMWF, and Dezső could be reading some new article, but actually that's not the case. What we see here is Dezső passionately reading the pub menu, and we are sitting in the famous George pub in Reading. Whenever he came to visit us several times. Whenever he came, this was our favorite place. So we never missed the opportunity to go to George pub to have a few pints. Now let's switch to the start of Dezső's professional career. So he graduated from Eötvös Loránd University in 1973 as a teacher of mathematics and physics, and as a secondary degree he studied meteorologist. His master's thesis was objective analysis of meteorological fields. So already at that time, in the early years of his career, his main interest was numerical weather prediction, and particularly data assimilation and objective analysis. Soon after his graduation, he had the opportunity to go to Leningrad for a postgraduate study under the supervision of the famous mathematician and meteorologist Lev Gangin, who was mostly known about his work on multivariate optimum interpolation. Actually, he was one of the inventors of this method in meteorology. So the title of Dezső's work in Leningrad was stochastic simulation of meteorological fields using Monte Carlo method. In more general, he was working on four-dimensional data assimilation. And the declared purpose of his visit was to get a candidature. So candidature was in the Soviet academic system the equivalent of what we call now PhD. Unfortunately, during Dezső's stay or around that time, Gandhin became a persona non grata in Soviet Union, something that in Russia called refushenik. So refushenik is, as probably you can recognize, the word is coming from the word refuse that was used for people who unsuccessfully tried to get permission to emigrate from the country, and when it was refused, of course, their career was over. So that was the case for Lev Gandhin, unfortunately, and it was also Dezső's bad luck because the cooperation and the supervision of his PhD work couldn't be continued, and he had to come back without the PhD degree. Patricia, Dezső's daughter, was so kind that she shared with me a few pictures from about the young Dezsős from the times that when basically none of us knew him. So the first picture, for example, surely I wouldn't recognize Dezső in his early 20s. Maybe the only thing that reminds me of the Dezső I used to know is the way he smokes the cigarette. Then the second picture is his wedding photo, so we see Dezső and Mary. Then on the third picture, Dezső with little Patricia in Hévíz. Hévíz is the small town near the west shore of Lake Balaton where Dezső's family is from. And on the last picture, Dezső is with his young brother Laci, who died at a relatively young age in his early 40s. So let's now move back to Dezső's professional career. When he came back from Leningrad, he became a scientist at the numerical weather prediction section at the Hungarian Met Service. Then for 5 years he was scientific secretary. So these were the times when I didn't know Dezső, so I can't say too much about his work from that time. In 1985, he became the head of a newly formed numerical weather prediction group at the Central Institute for Weather Forecasting, and that's the group that I joined 1 year later, so I know more about those times. Later in 1988, Dezső became head of weather forecasting division, also in the Central Institute for Weather Forecasting. The numerical weather prediction group was included in this section, so he continued on the scientific supervision of the activity related to numerical weather prediction. Here are a few pictures about these early years of Dezső. He traveled a lot, mostly to the eastern part of the world. So we can see on the left a picture from the mid-80s when Dezső went for more than a month to North Korea as a WMO expert. He was teaching the Koreans how to do NWP and particularly data simulation. Then the bottom picture, it is in Kazakhstan, so you see Dezső second from the right, and he's in the company of several famous Hungarian forecasters. You see Vichy Gyuri, who was the chief forecaster at that time, and then other forecasters. So that was a mission in Alma-Ata. So let's now concentrate on Dezső's work as head of NWP. So he formed this group of young meteorologists. He was the supervisor and he was training us on numerical weather prediction. The purpose in this group was to develop or adapt an up-to-date numerical weather prediction system. I wrote with red letters the adapt because that was Dezső's philosophy, and I think he was right that for such a small team like us, it is much more efficient to start with something not from scratch to develop a model. Moreover, it coincided with the situation that the Met Service had a new computer center So it was built next to the Central Institute for Weather Forecasting, and we had a relatively strong mainframe computer. I mean, in terms of the computer power available at that time. So that gave us the opportunity to adapt the model and even to have the target as an operational application of the model. In '88, Dezső and the director of the Central Institute started some negotiations with the Swedish Meteorological and Hydrological Institute, and as a result of that, the SMHI LAM system, which was their previous limited area model, became available for us. At that time, the Swedish already switched to the HIRLAM project, and they had this limited area model that was actually a grid point limited area version of an earlier ECMWF model. So they made this available for us, and Dezső was leading this project to adapt and operationally implement the model. We had visits from Sweden. Per Karlberg, their expert, came several times to help us to make the implementation. And from our group, István was the main person. He was the most experienced of us, so he did most of the practical work. And as a result of that, this so-called Swedish model became operational at the Hungarian Met Service in '91. Simultaneously, in 1990, Dezső represented the Hungarian Met Service at the kickoff of the Numerical Weather Prediction Cooperation meeting that was initiated by Météo France. So Météo France had the idea that together with some Central Eastern European countries, they develop a limited area version of their global model ARPEJ. So this is what later was called the Project Aladdin. At that time, they didn't have this name for that. And also in '91, it was Dezső and Mr. Mersis, who was the president of the Hungarian Met Service at that time. They initiated the cooperative status and cooperative membership to ECMWF. That was a long procedure, but we succeeded in the mid-90s, and as a result, Hungary became the first Eastern European country that could join ECMWF as a cooperative member. I have to mention that unfortunately, Hungary is still in the status of cooperative membership. Since then, many other Eastern European countries have successfully joined ECMWF. They are all full members. By now, Hungary is still only a cooperative member. I spoke about the Aladdin kickoff meeting. This is a picture in Paris, probably in front of the headquarters of Météo France in Paris in '91. So that was the start of this cooperation between Météo France, and at that time there were three Eastern European countries. So we see Dezső on the right, then in the middle, Jean-François Gellet from the French side. He was the head of the project. And then Radmila from the Czech Republic and Vladimir from Romania. These were the three countries that were contacted at that time, but very soon after that, a lot of other countries joined the project, and you know by now Aladdin is a huge international consortium. As you already at that time knew that he will not be part of the project because he already had the plan to start his second career in the US. Soon after that, he moved to Boulder, Colorado, as I will speak about in a minute. So I chose these pictures as an interesting moment of our life. So we made our first, actually for me it was the first visit to Reading. Dezső was there already once a year before. We went, Dezső and I, to Reading to IUGG conference in 1989. We were staying in London, so we combined as a private program with this mission. We were staying in a camping, as you can see on the bottom picture, in the outskirts of London, and we were commuting from there to the conference to Reading. So we took part at the IUGG conference. At least I had myself the first opportunity to visit ECMWF as well. And it was also a milestone in Dezső's future life because it was the first time he could meet his future bolder supervisors and friends, Stan Benjamin and Tom Sclatter. Now I would like to say a few words about Dezső as a teacher and supervisor. So between 1882 and 91, Dezső gave lectures for meteorology students on NWP. That was the continuation of another university course that was given by Tamás Prager, who was teaching dynamical modeling and the more practical part of NWP, like numerical methods, stability issues, Gagliarchy methods, then the state-of-the-art NWP models of that time and things like optimal interpolation. So these were presented by Dezső. Simultaneously, he was a supervisor for numerous master and PhD theses. He was not my supervisor in my master thesis, because when I started to prepare that, I didn't even know Dezső. Unfortunately, Dezső became our teacher only in the last year, and I started my work before. But since my subject was related to the statistical structures of meteorological fields, my supervisor, who was Judith Bartoli, introduced me to Dezső, and Dezső was very helpful. He immediately showed me a lot of articles from the Russian literature from Gangin and Kagan, and that was very helpful in my thesis. As it was already mentioned, he was co-author of a mathematical statistics textbook for meteorologists. So the title is Mathematical Statistics Methods in Meteorology. This is a book that is, I believe, still widely used by the Hungarian meteorological community. I would like to say a few words about Dezső's PhD work. So 2 weeks ago, I came to the library, and Marty, our librarian, was kind enough to lend me the PhD. Of course, I haven't seen that for 30 years, so I looked through again. The title was Application of Satellite Data in Objective Analysis of Meteorological Fields, and I believe the main motivation for Dezső, as he also writes it down with his own words in the introduction, was that at that time the numerical weather prediction models were rapidly improving, and as a result of that, the quality of the first guess fields used for data assimilation became much better. On the other hand, the temperature and humidity profiles that were retrieved from satellite measurements by retrieval procedures did not improve so much. So as a result, the use of satellite data in numerical weather prediction models was less successful than it had been expected a few years earlier. In the PhD, he introduces his two-step algorithm to filter and interpolate observational data, so-called robust filter method, and for interpolation he used biharmonic splines. But he also writes chapter about promising new methods that can fully account for the nonlinearities in the radiative transfer model, and in such way make it possible to directly assimilate satellite radiances rather than meteorological profiles retrieved from satellite data. So I copied one page from his PhD. It cannot be seen very well. The title of this page is adjoint-based method in data assimilation. So what he writes down here is basically 3D var. You can see perhaps in the middle of the page the host function, The notation is a little bit different from what we use now, but it's the same thing. And Dezső writes it down that this is the future and a promising new method. But at that time when he wrote his PhD, it was not used operationally anywhere. Even at ECMWF, it was in a very early stage to test the concept on shallow water equations. And the computer power, even at ECMWF, was far from being enough to run an operational 3D bar. So obviously at that time, Dezső couldn't guess that a few years later, he will be one of the key developer who took part in the implementation of a 3D bar system in Boulder, NOAA FSL. So now, perhaps I will switch to the second career of Dezső that started in Boulder. So these are pictures, you recognize it in front of this building, and on the top of this building, Stan Benjamin and Tom Schletter, who helped Dezső to get his job at NOAA FSL, came here to visit us. It was just a few weeks before Dezső moved to the US. And during this first visit to Boulder, Dezső was developing the rapid update cycle optimal interpolation in isentropic coordinates. So here we can see Stan, Tom, Dezső, and myself 35 years and 35 kilograms ago. I would just recall what Stan Benjamin said about Dezső last year when he gave this introductory talk. Dezső was the best data assimilation scientist in RAC Rapid Refresh Group at NOAA FSL. So in 1993, Dezső came back to the Hungarian Med Service. He became vice president. He was in this position for 2 years. Then he went back to Boulder. Then he came back again to Budapest. He became a professor at the Eötvös Loránd University, but then again he went back to Boulder. So his life in the 90s was a little bit like a pendulum. It looks he always wanted to settle back in Hungary, but when he came back, he always realized that once he tasted to be a developer scientist in a place where the conditions are ideal for doing such a job, he always wanted to go back, and until his death, in the end, he stayed in Boulder as a developer and scientist rather than a manager. I chose a few pictures from Boulder and from Budapest during that time. So here on the first picture, we see Peter Mandic and Vishy Gyuri. About Peter, I have to mention that he's of Hungarian origin, but he studied and worked in the US, and he was the head of the IT section of NOAA FSL. And the fact that there was a cooperation between the Hungarian Med Service and NOAA was to a great extent his achievement, together with Gyurka Major, who left already, and the president of the Hungarian Med Service, Mr. Mersic. So we can see Major Gyurka on the bottom picture, and then Dezső's family and Takácsági on the right-hand picture. So we have a few other pictures in 93 when Dezső came back. Stan came to visit us. On the left two pictures, it is us in Visegrad. On the right-hand picture, I said that there was this fruitful cooperation between NOAA and the Hungarian Med Service. And for example, Gisela spent a year in the US, and they helped us for some technology, IT technology transfer, and Tölgyesi Laci is there with Jeff Pedigo. Jeff Pedigo was a developer, software developer at the IT section, and he was a very good friend of Dezső. Actually, he came several times to Hungary, and he became a good friend of us as well. Even he visited me in Reading after Dezső died, and we had a few beers with him and Patricia to talk about the good old times. And on the bottom picture, Mr. Mersic, who was at that time the president of the Hungarian Med Service, he was visiting Dezső in Boulder, and they went to the Rockies. I also take these few statements from Stan Benjamin's last year's talk. So what were Dezső's main achievements in Boulder? Introduction of 3D VAR to know high-resolution short-range models. So this is something I mentioned already when I spoke about Dezső's PhD. Application of the community GSI statistical interpolation to the regional RAP model. Development of an ensemble-based closure scheme for deep convection parametrization, what is called Grell Dévényi scheme. Actually, this is something that made me really surprised, because I didn't know that Dezső had any interest in parametrization schemes. I just guessed that it was his deep knowledge of mathematics and statistics that enabled him to usefully contribute to the development of this parametrization scheme. And when I say that, I have to recall something that I experienced when I visited him in Boulder, and also when he visited me in Reading. Every morning he had a regime that he got up at 5 o'clock, and between 5 and 6:30 every day he was reading some mathematical textbook in the morning. So that was, of course, his hobby, but he was always looking for something that later can be successfully applied in his everyday work. So this is the last time when he visited us in Reading, so that was also on our cover picture. There were a few fixed points when he came to Reading. So one fixed point was the George Pub to have a few beers. So here on this picture we are with Erwin, our colleague in Reading, who's still working there, Dezső and myself. Then every time we went to a Premier League game, this time we went to see Birmingham, to Birmingham to see. That was actually a quite hard job for me. Every time he came to find some Premier League tickets. And the third fixed point was we always had to go to Oxford, to the biggest bookstore in the neighborhood, because Dezső was always after some new mathematical textbooks. So Dezső sadly died a few weeks after this visit, and then next summer, when Dezső had his birthday, we decided to meet up with his family and the very first group, NWP group of Dezső. So here we can see on the picture Dezső's wife Mary, and the daughter Patricia, and the young prodigy of the family at that time, Jenny dog, and us, the four young scientists who formed the first NWP group at the Central Institute for Weather Forecasting. So I think András will kill me. I do so much time.
No, this time not.
So thank you for the attention.
Yes, thank you, Gábor, and thanks for the thorough preparation. I spoke less at the beginning to give you a bit more time. You don't have to be too grateful, but it was okay, the duration. Thank you. So it was an appetizer. I think it was a good appetizer, and I hope you get a good appetite for the main course, the main dish, which will be delivered by Máté Miller. I had a look on your CV, so it seems to me that we can summarize your life in round numbers. You were born in 1985. You had your MSc degree of meteorology 15 years ago, 2008. Then you joined the Hungarian Meteorological Service, and you worked there 10 years, from 2018 to 2018. 2008 to 2018, and then you joined the meteorological, Met Norway, so Norwegian Meteorological Institute in 2018, and you worked there 5 years so far, and you defended your PhD September this year. And last but not least, you are the 10th award winner of the Dezső Dévényi NWP prize. So it's a pleasure to introduce you in this way, and his work is related to data simulation, which was at the heart of Dezső as well. Satellite data assimilation, which as Gabor mentioned, was also important for Dezső. And this is a work what Máté will present about satellite data assimilation for the Arctic region. So the floor is yours, and there will be opportunity for questions after this talk.
Thank you, András. So can I use a pointer? Good. So thank you very much. And now I would like to present my work, and the title is Advanced Assimilation of Satellite Observations in a Limited Area NWP System over the Arctic region. So here you can see the content of my talk. So first I will briefly explain the motivation, the objectives, and the background of my work. Then show you some of the main findings I had, and the future outlook, and close my talk with a final remark. So let's begin with the motivation. The numerical weather prediction over high latitude regions is special and particularly challenging. High impact weather such as polar lows, colder outbreaks are common here, making the maritime operation, transport, and everyday life difficult. National Met institutes and services made a successful collaboration to develop regional NWP models, which are portable to any region and applicable with very high resolution over a local domain. In order to keep the model on track with the true atmospheric state, observations are assimilated. And over high latitudes, the available in situ or conventional observations are sparse, so the satellite data assimilation is of high importance. However, satellite data assimilation in such a system, in high-resolution limited area models, is not optimal for several reasons, because there are limited data coverage, complex bias correction, the applied 3D VAR scheme is usually less developed, and the observations are considered as a fully representative information source for the model, and we assume that they are point observations in our assimilation system. However, representation error might exist, and this is the subject of my work, which I was trying to address. So the representation error, as defined by Janic et al. 2017, consists of error due to unresolved scales and processes, observation operator error, and preprocessing or quality control error. So here you can see a typical example of this error. We have a high-resolution satellite observation on the left, and we have a coarse-resolution simulated model equivalent on the right. So this error and the mismatch between the data and the model is generally explained from the global or low-resolution model point of view. On the other hand, there is also representation error in high-resolution limited area models. But the case is somewhat the opposite, so it can be described as an error due to unobserved scales and processes. So in this case, you can see high-resolution AROM wind vectors on the left, which is compared with coarse-resolution scatterometer ocean surface wind. So we have obviously a kind of mismatch between these two information. But this type of representation error is generally just neglected in our system. Assimilating the satellite data as a point observation is not optimal because the footprint of the satellite can or may extend over many grid points of the model. So instead of using those data as a point observation, a footprint observation operator can make the assimilation system more optimal. I will talk about that later. Beyond the representation error, there is an additional limitation which needs to be mentioned here. Since over the open ocean, it is not possible to analyze properly the small scales because physical constraints or forcing like orography or four-dimensional observations are not available generally. And if a mesoscale assimilation system has not enough constraint, dynamical model imbalances might appear on the small scales in particular, and this may interfere with the analysis on the large scale. By the use of a footprint operator, we cannot solve this issue, but we can attempt to make the assimilation system more optimal and use the few data we have. So here you can see the objectives of my work, which is basically to explore the satellite footprint representation in limited area high-resolution assimilation systems. And I investigated 3 different satellite observations, namely the scatterometer, ocean winds, wind profiles of aerial satellite missions, and microwave satellite radiances. It means that I also had to implement 3 footprint observation operator just to use those data in a more consistent or a more optimal way. This figure just illustrates the work logic and mentioned here that the microwave satellite radiance required the most complex footprint operator. So let's briefly explain the background of this work. And the subject is data assimilation, satellite data assimilation, where we have the goal to combine the observation and the model simulation in an optimal way. And data assimilation itself can be considered as a bridge between these 2 information sources. In the ARPEG, IFS, and AROM model family, the variational assimilation scheme became paramount. And in this scheme, we define a so-called cost function, J, where we have GB and GO subdivided costs, measuring the distance of the analysis between the background or prior model state and the observations respectively. So we can obtain the analysis where we have let's say, the lowest cost, or where we have the cost function at its minimum. And the link between the observation and the model is not trivial. And there is this observation operator H, which is responsible to map the information from model space to observation space. In this forward problem, the observation operator, if it's not appropriate, can be a source of representation error. For example, let's assume that we have satellite observations with a certain footprint, and if we have an observation operator which does horizontal interpolation to obtain the model equivalent of these observations, then we will have an inconsistent or not optimal assimilation scheme this way. So if we can construct or build a footprint observation operator which makes or which help us to aggregate or average the model high resolution model quantity over the footprint area, then this footprint operator can be a solution for the representation error. So I would like to briefly explain the 3 different footprint operator I had to implement. And the first one you can see here is for scatterometer ocean winds. And scatterometer data have a rectangular footprint shape, and a special footprint operator was implemented in the variational scheme to average the model winds in model space, and just trying to make the simulation system more optimal in this way. And also this operator, what we call supermodding, was implemented in a way that we can easily choose the averaging size we would like to target with the footprint operator, which was really useful to study the scales we need to target in the simulation system. So the second one is the ILUS footprint operator, and this one required a completely different approach or solution, because ILUS data have a kind of one-dimensional footprint size. So the raw ILUS measurements are just averaged along the satellite track, just to provide, let's say, a more accurate final ILUS product at the end. So with an ILUS footprint operator, I had to do a similar thing, just to make or just to find interpolated model points along the satellite track, and those what I can just average, or the footprint operator can average to provide a final model equivalent in the simulation. This is illustrated in this figure. And the third one is related to radiance observations, and for the radiance sensors have a circular shape footprint, and it means that the footprint operator needs to represent the satellite field of view in the observation space using interpolated model fields, and it forms a perfect circular shape at nadir, and when the satellite looks towards the edge of the spot, the satellite field of view and also the footprint operator point should form a more like an elliptical shape. So let's see now some results related to the first supermodding operator and the scatterometer data I studied. And here I would like to show you a case study where small-scale phenomena, convection, and the connected wind downbursts developed inside the aromatic limited area model. And what we can see this convection in the satellite image on the left. And if we see the wind fields from the arrow model, then it's somewhat apparent that the arrow model is able to resolve the amplitude of the mesoscale spectrum, but the downbursts and the convection patterns are usually just out of phase. And if we can zoom over this particular area, then we can see again this good example of the representation error, that the model is actually able to produce this small-scale phenomena, but we cannot expect to get or see something similar in a coarse resolution satellite product. So stay with the same case study. And now I would like to show you analysis increments. This is this first picture shows you the increments provided by the default scatterometer simulation scheme. And what we can see is that where we have the scatterometer observations, partly here, it shows a relatively sharp and detailed increment just by the use of the horizontal interpolation-based observation operator. And it means that the coarse resolution scatterometer observations constrain the small scales of the model, which is not optimal, as I just showed before. When we start using the footprint operator, the supermoding operator, we can see that the increment gets much smoother, meaning that the observation has mainly impact on the larger scales, and we do not correct or constrain the small scales of the model. So this is what we wanted to achieve. So now I'm showing here in a table standard deviation of observation minus background departures, which is a useful diagnostics to provide information on combined observation and background errors. So what we can see here is when we use the supermoding operator for the scatterometer data, then it can help to reduce the standard deviation of O minus B, which suggests that the system or the operator can help to remove the representation error from the system. And we can gain 4-5% reduction with 30 kilometer averaging size with this operator, which is more or less the footprint size of the scatterometer data. But we can also gain more reduction if we apply larger averaging sizes, up to a limit of 120 kilometer, more or less. So as a next result, observing system experiments were also carried out to verify the performance of this supermoding operator in comparison with the default observation operator. And here you can see plus 12 hour wind speed forecast verification. This is a normalized root mean square error differences, where positive differences means improvement by the supermoding operator. And what we can see here is that if we apply a 30 kilometer averaging by the supermoding operator, we can get a positive impact on wind. But if we apply 60 kilometer averaging size, the impact is even better, which is statistically significant for wind speed. And one might ask why we have the positive impact in this particular layer between 700 and 850. So we check this with a forecast sensitivity diagnostics. And it explains that if we have an impact near surface at analysis time, it propagates slightly upward during the integration of the model. So let's move on and see some results related to the ILUS winds and the related footprint operator. So here I'm showing again a standard deviation of O minus B statistics. And we obtained a consistent reduction in the standard deviation, which is indicated with these blue lines. Solid means the default operator, and the dashed line is the footprint operator. But the reduction in this statistics was much smaller, maximum 1%. And we have to realize that these ILUS winds have much higher observation error, which might explain this. We also had to conclude that the footprint operator is the most efficient when the variability in the model field is larger than the observation error. So scatterometer data is an accurate wind product, but this ILUS satellite, which was a pioneering mission, had this very high observation error. So this is just a polar law case study showing that the model variability over the ILUS footprint size is generally just 1 or 2 meters per second. So it's much, much lower than the observation error. Also, we did observing system experiments with this footprint operator, but we got mainly neutral impact on wind forecast. And this might be explained by the high noise level, as I said, of the aeroslated field winds, where we have the instrument noise much higher than the representation error itself. So let's move on and see the radiance footprint operator. So here, a prototype of the microwave cross-track scanning radiances were implemented and explored with MSUA and MHS radiances. So on the right figure, you can see just MSUA pixels over Svalbard and Barents Sea. And when we have the default radiance observation operator, basically we have just point information coming from the model. But when we start using the MSUA footprint operator, we have this spatial extend which we can use in order to obtain an average the model equivalent by the footprint operator. So as you can see that the footprint operator makes circular footprint shapes around nadir points, and when we move towards the edge of the SWOT, the footprint sizes and the footprint shapes is more closer to an elliptical field of view, as the measurement does. So here I'm also showing the footprint operator points for MHS data. So this instrument has smaller field of view size, and I'm just showing here 5 different scan lines. And this is just results related to surface emissivity. So when we start using more MSUA pixels and the footprint operator together, then we are able to retrieve the surface emissivity and to detect or capture sub-footprint variability in the emissivity field. And this is really useful if you would like to use radiance observations over complex surfaces or mixed surfaces. This is a picture over Svalbard region where we have also sea ice for this case study. I will skip this slide now and just jump directly to the statistics again. So I would like to show the same standard deviation of O minus B statistics for the radiance footprint operator. You can see this as a function of MSUA and MHS channels in the top panels. And you can see the standard deviation as a function of scan positions for MSUA and MHS. So we can conclude similarly to ILUS and scatterometer data that the footprint operator can reuse the O minus B standard deviation. So this is good, but it's worth mentioning that the radiance footprint operator has an increased computational cost as well, because the current implementation uses the radiative transfer model several times. So for a single radiance observation, the radiative transfer model is just called several times to get this spatial or this spatial extent of the model equivalent. So the optimization work is still ongoing and becomes essential if you're thinking about operational implementation in the future. So let's move towards future outlook. So in a high-resolution, state-of-the-art simulation system, I believe advanced solutions like super-robbing or footprint operators are required and important to reduce the representation error. And in the future, I would like to continue the development of the radiance footprint operator to take into account the satellite antenna pattern, and also to not just to represent the instantaneous field of view, but the effective field of view of the satellite. And also I think this kind of operator can be used in other areas, like in ensemble prediction system, for example, to take into account the uncertainties in an EDA system which is connected to representation error. And one might design a method which can generate perturbations in this way. And this is just a slide mentioning that the future plan is to combine this operator with a more advanced simulation scheme, for example, 4D VAR. And in the harmonium system, the usual 4D VAR scheme is based on a multi-resolution approach. So we need to change the sampling resolution of the radiance footprint operator just to match the coarse resolution minimization in the 4D VAR. And now I would like to stop here with the presentation of my work and just make a final remark about Dezső Dévényi. So unfortunately, I didn't have a chance to know Dezső Dévényi in person. However, I remember his scientific books filled up the office where we have been working, and when I started to work as a newcomer in OMS, so I particularly remember that many books were from this publisher called Dover. So when I started as a newcomer, I'm just watching those books day by day, and I have to tell that I hardly understood the title of his books because many of them were too abstract. But it helped me to felt much respect toward his knowledge and his legacy. Just wanted to share this with you. And at the very end, acknowledgement, I would like to thank for colleagues in the NWP group at OMS for the encouragement and also for the common work in the past. And I would like to thank for the selection committee. And finally, thank you for your attention.
Yes, thank you. So, yes, so we have time for some questions here in the room and also from the online participants. And before that, so I think your work demonstrated very well the links. Of course, the last slide was very nice because, as Gábor said, that Dezső was addicted to have new and fresher books on mathematics. And for the family, it was impossible to keep them after he passed away. And they offered to the Hungarian Med Service. And first of all, it was offered to the people who work on NWP, including Mate. And the other thing, until you think about questions, that it's nice to recognize that in the Hungarian that society meeting before this this event, it was recognized that how much Dezső contributed to the lectures in the university for the students. And I think this was a prime example that Máté, in fact, who was using this information and to learn this in the same way as Dezső taught us, and what we extended afterwards, could use in the practice, and you could use it in your PhD work, and hopefully it will be used in the operational context as well. So, spoke a lot, so you have time to think about questions. And Gabi, if you can help us if there is anything online on the chat or any question on the here. So I can give you more time to think, so I have a question. So, Máté, you said that there's a limitation due to the fact that you have to run the radiative transfer model several times. So that is which prevents you to use it in the operational context for limited area model. And the other related question that how this can be used in the full context of the operation WP. You might use it in the global context as well. So what is the best combination to it? So the first question is more about how it can be exploited operationally from practical point. The other is how the global and then the limited area cohabitation and the relations can be the best and optimally exploited using your method.
Yes, so this third footprint operator for radiance data, so this can be implemented in many different ways, but what I've chosen is the most expensive, let's say, which does the averaging after the radiative transfer calls. So it means that for a single, let's say, M3A pixel, we need more than 100 additional points to have the final average model equivalent. And it helps us to take into account the nonlinearity in the radiative transfer simulations. But it can be done differently to make the averaging before the RT-TOF call. It means that we just average the model quantity before the RT-TOF simulation. And that would mean just to call the RT-TOF again just once for the averaged model quantities. And that immediately helps to speed up this operator, but we lose something in terms of nonlinearity involved in the radiative transfer simulations. So there is room to optimize this further, but as a very first step, we wanted to make an operator which is really fancy and expensive at the same time, but we can see perhaps the biggest benefit in terms of impact on forecast. And one completely different solution is to forget to use this expensive footprint operator and address this representation differently, which is a new fashion now to apply data-driven approaches and machine learning and calculate or determine this representation error offline and just remove from the system without making expensive footprint representation in the observation operator. That's an alternative and probably a much faster way to eliminate the representation error. Yes. Yes.
Yes. Everybody from the virtual space? Any question? No. Maybe we can go to the next point, which is the ceremony of presenting the award. So Martin, if you present yourself, please. This would be a presentation and comment. Okay, so Gabo has the full stand and W record. Yes, take up the photo. Yeah, photo for the record. So Gabo is under see online. So Gabo is not presenting the diploma, the result. Thank you. Here, there's a question. If not, then I have the obligation to close the meeting. Thank you very much, Martin, first of all, for applying and for succeeding and for presenting. Thank you very much those who took the time to come, especially this day, possible day in Hungary, Budapest. Thank you for those who joined us, especially the US colleagues who woke up very early to be able to join. Thank you. Have a nice evening and have a nice day for those